All right. Ready, set, go. Okay. So if I were, you know how you guys, we started talking about two types of compounds, and if I were to ask you what are the two types of compounds? Starts with letter M.
Molecular.
Right. Very good. Molecular compounds and ionic compounds. Very good. And you have a list of stuff about those two things. You know, we can kind of compare things about molecular compounds and ionic compounds. I just want to kind of make a point here that your lab, the lab we did Thursday, what type of compound do we focus on? Right, ionic compound. So my point here is just simply to say we talked about lab was your nomenclature, which is basically naming and forming ionic compounds. Okay? Right. Now, I mention that because now we're going to switch gears. The title of this is covalent bonding. Covalent bonding. Here we go. In covalent bonding, I'll just write it under the title. I think it's up the next slide. Electrons are what? Shared or transferred? Shared, exactly. Okay, electrons are shared. What sort of compound has only covalent bonds? Molecular, exactly. Only covalent, electrons are shared, chemical bonds. And then I think I said for ionic compounds it has at least one bond. That's ionic. Okay, so I just kind of wanted to kind of set the stage for what we're talking about. We're kind of switching gears. Okay, so we're going to talk about how those electrons are shared. Now, we didn't talk about the scientific theory in here, or the method of the scientific method. Scientific method. But are you guys okay that if somebody says it's a theory, that is not just a guess? Are you guys okay with that? Okay, good. Because basically if it was a guess, which probably wouldn't be a guess, it would be a hypothesis. So hypotheses are elevated to theories. Okay, so electrons are shared. Let's talk about electrons being shared. Oops, sorry. So a covalent bond is formed when atom A and atom B, and I think I gave you an example when I talked about water is a type of molecular compound, and a cute little oxygen in the middle shares electrons with the two little wingy hydrogens, okay? It's wonderful, okay? So that forms covalent bonds are a type of chemical bond, okay? Sharing of electrons. So again, two types of compounds, molecular compounds and ionic compounds. A synonym for molecular compound is a covalent compound. And it's kind of consistent with molecular compounds have only covalent chemical bonds. Okay, only. If you take a magnifying glass and look at the chemical bond connecting the atoms. Electrons are being shared. Electrons weren't transferred. Now, we did already talk about kind of electronegativities, and we said that it's possible that they share electrons but not evenly. And we talked about actually you can have a degree of polarity. Electrons not transferred, but one is slightly more negative than the other because of its higher electronegativity. So this is kind of a review slide when it comes time for the two types of chemical bonds. By the way, the two types of chemical bonds form, how do I say this? At the crux of why they form is because the atoms want a complete set of 8 electrons around them. Okay? So we'll kind of keep that in mind. So I told you on your unit exam, whether it's a week from Thursday or 2 weeks from Thursday, on your unit exam, I said one of the things I'm going to do is give you a section with just chemical formulas, and you're supposed to tell me if that's an ionic formula. If that's a formula that represents an ionic compound, or if that formula represents a molecular compound. And you're going to look for the metal. It's like there used to be, look for the metal, okay? And if there is a metal there, then it's probably an ionic compound. And I encourage you to use the periodic table. It's kind of like the look for the Union label. It's like an old commercial. Anyway. All right, so we're talking about covalent bonds, electrons are being shared. So if electrons are going to be shared, then remember we talked about that thing called delta chi, or electronegativity difference. And kind of on that scale of electronegativity difference, remember how this works is we have atom A going to be joined with atom B. This is my bond. I don't know what kind of bond it's going to be. And I told you to look up the electronegativity of A, and you guys actually did good doing the homework like this. Okay? And you said if it's less than like 1.7, right, then an electron's going to be shared. They're not going to be transferred. Right. So these are kind of the non-metals that tend to kind of be stuck together. If you kind of pick a couple of them and look at what sort of electronegativity difference you get, hopefully it's less than 1.7. Okay, sometimes they kind of push the limit here. Okay, but these are non-metals joined together to make molecular compounds. Or I guess I should say these are non-metals joined together to share electrons and make at least covalent bonds. And actually for your lab on Thursday, when I walk you through how to make structures, one of the things that's going to be important is to find the middle atom. We're going to do a lot of just kind of, our structures are going to be kind of simple. They're called Lewis structures. It'll be pretty simple. It'll be something in the middle and stuff kind of branching off of that. The thing that's in the middle is going to have the lowest electronegativity, so you're going to want to remember this. Okay, so electronegativities for the metals and the nonmetals, electronegativity increases from left to right and increases from bottom up. So you're going to want the lowest one. So I'll remind you that. All right. So the two atoms that went together to be chemically bonded, okay, whether they transfer electrons or share electrons, they're trying to get a complete octet. Okay. The rare gas electron configuration is octet. Some of you guys, I know, have had chemistry before. This is octet. Of course, the word octet kind of gives it away, 8 electrons, right? So electrons aren't transferred, electrons are shared. But if we look, I think I'll pick on the water molecule again. Let me go ahead and kind of show you what I put up before. Of course, you guys would tell me water is H2O. Okay. The Lewis structure for water looks like this. We put oxygen in the middle because hydrogen never wants to be in the middle. And kind of before I showed you this, let's see, how do I say this? Well, let me go ahead and do this. When we draw our Lewis structures, one of the things I'm going to remind you of is we're going to start with those special electrons, the valence electrons. So for oxygen, we know it's valence electrons if we look at the group that it's in. So it's in 6A, so here we go. 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay? So hydrogen is atomic number 1. It only has 1 electron, and that 1 electron is a valence electron. So the hydrogens kind of saddle up to the oxygens like this. And I'll go ahead and use red circles for that valence electron around a hydrogen. So when it talks about double dipping, I mean, it's a beautiful thing in that actually this pair of electrons serves the hydrogen, and that pair of electrons, it's like joint custody, serves the oxygen. So the things that I'm circling here are the electrons that are being shared. Notice in this case, 1 electron's coming from the oxygen and 1 electron's coming from the hydrogen, but it doesn't have to work that way. So can you see in doing so that by the hydrogens kicking in an electron each, that if I circle all of the electrons around the oxygen atom, okay, now we got 2, 4, 6, 8. Okay, that's its complete octet. Now, hydrogen, not so much. Okay, if I just circle hydrogen, okay, it's only got 2 around each of it. But if you look on top of neon, of course, helium is a rare gas. And so 2 electrons is like helium. So hydrogen does that. So that's kind of when we're talking about electrons being shared. Now, every rule was, rules were all made to be broken in one way or another. And so when I talk about a complete octet, okay, the problem with boron, or the reality of boron, is when you look at how it's connected with other stuff, it's not going to want 8, it's going to want 6. Okay? So that's boron. So these are exceptions to the complete octet rule. So boron just wants 6. We don't do a lot with boron for obvious reason because I want to focus on an octet. The other thing, and we'll dabble just a little bit in this, but it's quite possible anything that's heavier than period 3, and you're like, dude, that's a lot of stuff. Because beginning with potassium, okay, that's period 4. So you're like, that's a lot of stuff. Anything beyond that actually can have what we call an expanded valence. And again, we won't in this course really kind of focus much on that. But what an expanded valence means is instead of an octet, and it'll still be in pairs, they'll want a set of 10 electrons around them, heaven forbid, or 12 electrons. It's called an expanded valence. Okay? So 10 or 12. All right. So the valence bond, I thought of Cameron when I said that. The valence bond theory. Okay. Valence bond theory goes like this. Okay, so electrons are going to be shared ultimately. So here's the deal. We talked about how do you find homes for electrons around a neutral atom, and we put them in boxes, okay? And those boxes we called orbitals. Those were the atom's orbitals. Those were atomic orbitals. So here's the deal, basically, and they're S, P, D, F, that sort of thing. They kind of come in kind of cool shapes, right? Spherical, dumbbell, and then they get strange from there. But basically, think of the atom A and atom B, who wants to make a covalent bond between them, basically sending out one of their atomic bonds, okay? And basically, they will overlap and form another, their orbitals. They send out one of their, each one sends out an atomic or a bond orbital, okay? There's an overlap, and that's actually where the bond orbital is. So atomic orbital, overlap, bond orbital. So this is kind of how I picture that. You know, atom A and atom B just wants to share a pair of electrons. Well, to share a pair of electrons, they need to form a place for those electrons to hang out. Let's pick on the kind of the dumbbell shape, like if that's the nucleus of A, and this is a p-type orbital, okay, a p-type orbital, okay? So those are atomic orbitals, what I drew in purple, and where they overlap, actually they have created a bond orbital. So those pair of electrons that were like between the oxygen and hydrogen, that's where those electrons are. And actually there's what we call a differing amount of strength in these covalent bonds. Sometimes the overlap is great, and sometimes the overlap is just barely there. And actually, that translates to how strong a covalent bond is. Not all covalent bonds were created equally. So, valence bond theory. By the way, see the title is A Simple Quantum Mechanical View. Nothing in quantum mechanics is simple. If you're familiar with, to me, it went like Newtonian physics, okay, and then it went quantum physics, okay. So Newtonian mechanics, quantum mechanics, and now it's kind of string theory, which I don't know if that's going to hold on or not, okay. But anyway, it's pretty cool. So valence bond theory. What else do we need to know? Valence bond theory. Well, that line, so here, usually, I think I told you before, if I draw a structure, if I draw A, line, B, okay, my solid lines are covalent bonds. So anytime you see a line in my structures, actually that is a pair of electrons. That's a covalent bond, pair of electrons. And there, and we kind of saw that between the oxygen and the hydrogens, right? And right there, what this is saying is whenever you see one of those, I want you to think 2 electrons, not only 2 electrons, but 2 electrons in now a bond orbital, right? There's my bond orbital. And we know when we shove 2 electrons in an atomic orbital, they need to have opposite spins. And that actually is the same thing here. Isn't that kind of fun? I think so. Now, I'm kind of giving you a lot of background, which you may or may not need to know, but I think it's helpful. And this last thing, or I don't know if it's the last thing, but another thing is that pair of electrons that actually hang out in that bond orbital, they can come from both from the same atom, or like in the case with water, they can come from different atoms, but it's only 2 electrons. All right. So I brought actually some things today. And we're going to pick on compounds that are called hydrocarbons. So they contain only hydrogen and carbon. And the simplest of them, well, I guess not the simplest of them, but if you want to have 2 carbons, like in what we call the carbon skeleton, there's this one, carbon, it's C2H6, and it looks like this. Your 2 carbons go like that, and your 6 hydrogens go like this. C2H6. Right. So each of those lines is a solid line is a covalent bond, and think of a pair of electrons. And then the cool thing is we could go ahead and pick on any of these, because these carbons are like the same, aren't they? Let's pick on a carbon, and let's go ahead and draw a circle around it. And if I draw a circle around that carbon, each dash is 2 electrons. So can you see where that carbon has 2, 4, 6, 8? It has 8 electrons around it. It has complete octet. The other carbon does too. Okay, so let's look at a double bond. And the formula for something that has a double bond, a hydrocarbon, is this, C2H4. And C2H4 looks like this. It has carbon, double bond, carbon, and then the 4 hydrogens are 2 on each of the carbons. Okay? You've probably seen this before. You know, carbon, double bond, carbon. Now if we draw, and those are symmetrical too, by the way, but if I go ahead and draw a circle around a carbon, each covalent bond is 2 electrons. So we have 2, 4, 6, 8. 8 electrons. But it's this is kind of fun. See, look at this. But those 4 electrons that are making, so there's 4 electrons right here in a double bond. That's what this says. Okay? A double bond results from the sharing of 2 pairs of electrons. See, 2 pairs, that's 4, right? So we have 4 electrons right there being shared. Last but not least, triple bond. Dun, dun, dun. And I'm going to put it right next to my double bond one. The formula for this one would be C2H2, and it would look like this. Carbon, triple bond, carbon. And we only have 2 hydrogens, and not so surprising, they're going to kick off of the carbon. So if, again, we draw a circle around either one of those carbons, can you notice where this carbon has 2, 4, 6, 8? It has a complete octet. Okay? And so does this carbon. But the point here is that anytime you see a triple bond like that, you're sharing 3 pairs, or what, 6 electrons, right? Oops. There it goes. Any questions? One of the things, and we'll talk about it in lab, but one of the things you're going to want to be able to do for your unit exam is to interpret a Lewis structure. And this is kind of one of the things. All right. Well, not all covalent bonds are created equal. There's 2 types of covalent bonds. I sometimes call this one the first to arrive. Oops. The first to arrive. And to me, it works okay because actually it's called the primary bond. First to arrive. First on the spot. So honestly, what this tells you is if you have 2 atoms that are stuck together with a covalent bond, and it's a single covalent bond, that one is what we call a sigma bond. Okay, sigma. That's a Greek letter. The lowercase. All single bonds are sigma bonds. So the first structure that I drew before, the C2H6, guess what? They were all sigma bonds. Okay. So yeah, see Aaron looked over here. This one is C2, so black is carbon, and on your lab, when you do your lab, you'll be actually having to get to make your little models. I don't have enough of these, but, and I'm not picky about color, but yeah, these are carbons, and you can kind of see the 6 or the 3 hydrogens and the 3 hydrogens, okay? Now the bottom thing here, so I'll pass this around. I'll keep everybody awake. Do you see where basically those gray things, as it comes around, those gray things are actually the sigma bond orbital, okay? That's where a pair of electrons are. That's the sigma bond. And so when this says it kind of orients itself between the nuclei of the atoms, that's it. Well, if that's the first to arrive, and this actually is kind of funny, after you have your main course, you can get dessert, and the type of dessert is pie. Yeah. So this type of secondary bond, it's a covalent bond, electrons are shared, okay? But it's only after you have your primary sigma bond can you have your secondary pi bond, okay? So here's the deal. When you have a double bond between atoms, the second to arrive, the second line is a pair of electrons that are participating as what we call a pi bond. Okay. Triple bond, guess what? The first one to arrive is sigma. The next 2 are both pi. Okay. So if the pair of electrons for the primary bond are buzzing around kind of like the sweet spot connecting the A and B atom, where are the pairs of electrons that are the secondary bond? Well, they have to actually lie outside. It's kind of like a hot dog bun. Like this is the hot dog and this is the hot dog bun. Okay. So this is C2H4. C2H4. So on the structure, you had a sigma bond and a pi bond between these 2 carbons. Well, you recognize the gray sigma bond. The pi bond actually needs 2 colors to represent, because actually that pair of electrons that are in that secondary bond are buzzing around kind of in a sandwich sort of situation like this. Okay, so that's C2H4. So we have sigma, pi. Then the last but not least, we said that's a double bond. What about a triple bond? Well, this is a triple bond. So we have the black carbons. Between the carbons, we have that sigma bond. That's the gray thing. Okay, then we need to have 2 bond orbitals with 2 electrons in each outside of that area. So pick a pink and a purple, and a pink and a purple. Okay, that's 1 pi bond, and that's another pi bond. So pi, pi, sigma. Of course, sigma first, and then pi, pi. That's your triple bond. Now, as I have this up here, does it kind of look like a stick? Okay. Actually, the presence of a triple bond in this case actually gives, we're going to talk about actually geometry around an atom, but it forces the geometry, this triple bond. The double bond force, this actually is something we call linear. The double bond, in the case of that molecule, for something we call trigonal planar. With everything sigma bonds around a given atom, a carbon atom anyway, that actually was something called tetrahedron. So we'll talk about that more. So there's your hot dog. That's C2H2. Sigma bonds first to arrive, primary, pi bonds secondary. But pi bonds are pretty important because, like on the double bond and triple bond carbons, they needed to do that in order for those carbons to get a complete octet. So definitely it's a possibility. It's not that special. So there's what we call the expected, I usually put the word expected valence of an atom. And oftentimes expected valence of an atom, and I usually say it's the number of times an atom reaches out. And I'll try to tell you, actually it's in the definition here, reaches out. And I kind of think of, this is not very mature, but I kind of think of like an octopus or something reaching out. Okay, so if the middle of me is an atom, Okay, this is the number of times it expects to reach out. As I wiggle my arms, when I'm reaching out, in this case, the expected valence of an atom, I'm talking about I can only connect up with those two types of bonds we talked about. Sigma bonds, it's kind of that circle with a little thing like that. And of course, everybody knows the symbol for pi, especially this year, right? Okay, so sigma, primary, and pi bonds, secondary bonds. Okay. So, the expected valence of an atom, goes back to the group number again. Okay, so we're kind of building up. Remember, the group number is important to kind of set the stage for what that column of elements are going to do. Okay, so basically what this says is you look at the group number, you take 8, and from 8 you subtract the group number. Okay, so I don't have which is kind of cool. So what's the last group over there? What's their name? Noble gases, very good. And what group number are they? They are 8. What's 8 minus 8? 0, exactly. So for the noble gases, or rare gases, either, whatever. So there, you take 8 minus, I'll go ahead and put it Roman numerals like this. 8 minus 8 is 0. So guess how many times they like to reach out? 0. 8 minus 8 is 0. Their expected valence is 0. Okay, what's the name for the group right next to them, right before them? Halogens, very good. So if we take, for the halogens, okay, they're group number 7. So if we take 8 minus 7, that equals 1. They're just going to reach out one time. Okay, and then, of course, that's the fluorine, chlorine, bromine, acid, iodine. So we go over 1, beginning with oxygen. Okay, so 8 minus, this is for oxygen, I guess I would do. 8 minus, actually they are group 6, oxygen's group 6. Okay, 8 minus 6 is equal to 2. They're going to reach out twice. Okay, etc. Oh, but, sorry, before I go on, actually you're going to see it summarized on the next table. And this is important. Hydrogens only want to reach out once, and it's going to be a sigma bond, right? First to arrive. Okay, and boron wants to reach out 3. Does this make sense? It wants to reach out 3 because it doesn't want an octet, it wants 6. So that's how the 3 kind of comes out for boron. So here's kind of a summary. So if I were to write the group numbers over here, you told me for the halogens it's group number 7. For oxygen it's group number 6. For nitrogen it's group number 5. For carbon, it's group number 4. There's like on QuizUp, there's all sorts of different categories, and there's a QuizUp category for like Roman numerals. You're like, really? So anyway, I'm trying to get better at this. So any questions about this? Now, go back to those structures, those 3 hydrocarbon structures with the all single bonds and the double bond and the triple bond. Can you see where, and I'll just kind of do it right here. Can you see where, if we skip ahead to the carbon triple bond, carbon, actually, this, in all of those structures, it's following carbon's expected valence. The times it's going to reach out with sigma and pi bonds is always going to be 4. That's its expected valence. And we'll talk about there are some times it doesn't follow its expected valence. But can you see, in this case, carbon, in all of your cases, carbon's reaching out 4 times. All right. So this expected valence, actually, it kind of makes sense if you look at those Lewis dot formulas. Okay. Remember what Lewis dot formulas are is basically you write the symbol of the element and you assume that that's the nucleus and all the non-valence electrons. And then you put the valence electron dots around them. And I think the other day I kind of teased, you can kind of think of a car kind of going to park. Car's going to park here, car's going to park here, here, and here for carbon. For nitrogen, it's going to park here, here, and here. Okay. Expected valence of carbon is 4. Expected valence of nitrogen is 3. Expected valence of oxygen is 2. Okay, so those are going to be your covalent bonds. Sigma, the primary, or the secondary pi. All the halogens have electron dot structure like this. Okay, and of course neon is like, dude, garage is closed. No more vacancies. Okay, I added, and I don't know, it's up to you if you want to add it, but I added the word pot of this morning because I use that word a lot. In lab, when you guys start drawing your Lewis structures, like the 3 structures with a single, double, and triple bond between carbon, those are Lewis structures. You guys are going to be drawing your own Lewis structures. And I'm going to talk you through it step by step. And the first step is to come up with a pot of valence electrons. Pot of valence electrons that were brought to the table by all of the atoms in the molecule. We can also draw Lewis structures not of just molecules like the C2H6 and the C2H4 and the C2H2. Those are molecules. But we can also draw Lewis structures of your polyatomic, bless you, ions. The ones that you guys are working on memorizing. The nitrate, nitrite, sulfate, sulfite, hydrogen, sulfate, hydrogen, sulfite. You know, you can draw those Lewis structures too. So we're going to come up with a pot of valence electrons first. And those valence electrons from the pot, you have to use your entire pot. You have to end up with nothing. And those electrons will be distributed on your Lewis structure. Okay. And the thing about it is they'll be a line. Remember, we've been talking about lines. The lines will be a pair of electrons. It will be either a sigma or a pi bond. Okay. But the other thing, quite possibly, with those valence electrons from your pot of valence electrons is sometimes they end up, and I usually go dot, dot. They basically end up on your Lewis structure and actually around the molecule, okay, around a particular atom in a molecule, as what we call a pair of lone pair electrons. A pair of lone pair electrons is what I usually call it. Okay, they're dot, dots. A pair of lone pair electrons. And they're important because they help add the octet to that atom. And they were in your pot of valence electrons to begin with, so you can't ignore them. So that's kind of how that works. So the Lewis structures, and again, the ones that you've seen this morning, we're going to look at a few other Lewis structures, but like when you draw carbon, single bond carbon, you know, and then that carbon has 3 hydrogens and 3 hydrogens. Okay, think of those, the symbol for the element, kind of like the symbol for the element in your Lewis dot structures. Basically, it's the nucleus of that particular atom and the non-valence electrons. We talked about the second one, the fact that solid lines in here are a covalent bond, a pair of electrons are hanging out, being shared between those 2 atoms. If you do have and those are sigma bonds, single dashes are sigma bonds. If you do end up with a structure that has 2 dashes, of course that's a double bond. The first to arrive is sigma. The second one is that secondary pi bond. 3 dashes this morning we said the first to arrive is sigma. The next 2 pairs, which is 4 electrons, right, are going to be actually pi bonds. And I'm going to show you a Lewis structure that has a dot dot, okay, a pair of lone pair electrons. And actually out there in the real world there are cases where the lone pair is just a lone single one, but ours are always going to be paired electrons. And we talked before that kind of hold this whole left, right, top, bottom, or north, south, east, west. There's no significance there. So I think it's, and I don't know if you'll catch this wave, but I just think it's really cool that the Lewis structures you draw, that we come up with paper and pencil, that is the real deal. That's really how that molecule is, or that polyatomic ion is. And in chemistry, biochemistry comes to mind. Really, the shape of something, what it is in 3 dimensions, is very, very much a player in how we interact with it, for instance. So although we have 2-dimensional paper and pencil, Actually, I'm going to try to convince you, maybe a little today, but probably more in lab, that you can basically lift off the paper in your own mind, or make one of these, and you can kind of see the three dimensions. So, for instance, that C2H6, it didn't look like this, but this is really what it looks like. And it's kind of cool. There actually is what we call free rotation around any single bond. Okay, awesome. You go ahead and get a secondary bond. This is the C2H4 rotation. I don't think so. Okay, so it's real. It's basic, but it's real. Okay, so one of the GERs I have at this point in the course a little bit is we talked about ammonium. I don't want to confuse you guys, but ammonium is one of the things you're supposed to memorize. NH4 plus 1. Yeah. And I think I kind of growled about this on Thursday. There's also this important molecule. This is a neutral molecule, and it's called ammonia. Some related, don't they? NH3 neutral. I'm going to kind of give you a precursor at how you can come up with this. I talked about the pot of valence electrons. Let's go ahead and take a look at what the pot of valence electrons for NH3 would look like. Okay, nitrogen, and this is what I'm going to do it on Thursday. Nitrogen, there's one nitrogen atom. And any nitrogen atom, and this is why you need to have a periodic table handy, any nitrogen atom is going to have 5 valence electrons because it's 5A. 5 valence electrons. Any nitrogen atom. 1 times 5 is 5. Hydrogens. There are 3 hydrogens, and any hydrogen is going to have 1 valence electron. Does that make sense? Only has 1 electron in it. It's special. It's valence. Okay. So when I keep talking about a pot of valence electrons, okay, just from the formula, can you see that we have 5 plus 3, or we have 8 valence electrons? That's our pot. Now, someone went ahead and distributed those 8 valence electrons around on the final Lewis structure right here. Okay, but can you see where there are 2, 4, 6, 8? Okay, there are 8 valence electrons. There are 8 electrons represented there. And just so we're kind of all on the same page, I brought these. Okay. And they probably need to be repainted, but that's okay. Instead of carbon, let's make this nitrogen. Okay. And so I need 3 hydrogens. And yeah, it's a spatial thing. It really is a spatial thing. They're like, Mrs. Snake, why are you making them do that? Well, that's because that's what they do. So NH3. And what's this? That's what? Yeah, exactly. Those are my lone pair electrons. Exactly. Is that not cool or what? That's what ammonia is. Water. Let's see. If you go back, we could do, I want to show you the thing for water. Remember earlier today we did this? But if you look at what I did, that's water. So here we go. I know, I'm like alchemy, right? So it was a carbon, then it was a nitrogen. Now I'm going to make an oxygen. Okay, oxygen, hydrogen, hydrogen. Lone pair electron, lone pair electron. That's the shape of a water molecule. Is that not cool or what? Actually, that has consequences. It's a small thing, but that is no small thing. It's just so cool. I know, I'm easily impressed. Formaldehyde, it has 4 atoms, 2 hydrogens, 1 carbon, and 1 oxygen. I'm not going to do it now, but we could come up with a pot of valence electrons, and it looks like 2, 4, 6, 8, 10, 12. 12 electrons. You buy that? That's what you would get. Kind of reverse engineering, right? 12 valence electrons from those 4 atoms. And one of the polyatomic ions you're supposed to memorize are for all of the halogens, except for fluorine, I guess. They form 4 forms with oxygen. This is the simplest, so it ends in "ite" and it has a prefix hypo, so hypochlorite. And that's what hypochlorite looks like. Again, 2, 4, 6, 8, 10, 12, 14. 14 valence electrons. We can do a quick check. For chlorine, there's 1 of them. Chlorine is a group 7A element. 7 electrons. Oxygen, there's 1 of them. And oxygen, we said, is group 6A. Okay, so 6 electrons plus 7 electrons is 13 electrons. What did I say, 14? Okay, so the pot is here, almost. What we need to do is add actually 1 electron for the charge. Okay, so actually that's why our total is really 14. But does each atom have a complete octet? Yep. Sigma bond between them. Okay, so these actually are going to be due after you do your lab. I'll remind you. Okay, so the lab's on Thursday, and these will be easiest to do. I know that's setting you up for a lot over the weekend, but that's the deal. So I think we'll stop there, and that gives us a good position for Wednesday's lecture. So nothing due Wednesday. Give me a chance to catch up grading your stuff.